So I've been working on a lot of circuits lately, of course, as you've seen on the channel, including my last one, which was this memory chip, which I addressed and then was able to read and write bits from it. And I've been thinking about what to do or like where to go next. And I have an idea in mind, but I'm not going to share it just yet because I don't want anyone to come in and explain exactly how to do it. I want to try and figure it out. For this video, I want to put together a piece that I think I'm going to need for my bigger project idea. And that is a timer that I can get a clock source from that lets me start and stop it and even step it individually. And I went down the road of trying to maybe figure out how to make that myself because it didn't seem like it would be that difficult. But I forgot about things like debouncing switches and stuff. And then I remembered a video I watched many years ago by Ben Eater, who has already done this. I mean, he's built an entire computer with breadboards. It's pretty awesome. But he has a kind of a standalone circuit for running his clock that uses 355 timers in different ways. And it has exactly what I think I need, which is a timer that goes continuously and a way to switch between automatic and manual. So I think for this video, I'm going to mostly just hook his up and then using his schematic, and I'll walk through it though, to hopefully I can understand how it works or talk about how I think it works. He had some videos on the topic, but I haven't watched them for years, so I might be completely wrong, and I'll go back and watch them later maybe. After I get the clock built, then what I do want to do, in hopefully in this video, is connect it to a 8-bit counter that I have, which again, I've done something similar to that before with this, but this was in base 10. And of course, where I'm going with this is my circuit idea is going to involve the memory chip, but I need to address it over time. And so what I'm hoping to do is to build a counter that counts up with 8 bits, which I can use as an address on my memory chip here for the next phase of this project, if I can figure out how to make that part work. But for this video, clock source, counter, and probably some LEDs so we can see it working. Maybe this will end up being a short video because, I don't need to talk about the 555. Ben Eater did a better job of that than I ever would, and I'll just do the highlights and probably zip through connecting it, and we'll see how it goes. Ben's site actually has a small page here dedicated just to the clock module, probably because it's very useful all by itself, and he has links to his videos. I'll put a link in the description too. And here's the schematic of his. Okay, so I opened it up in a separate tab so I can zoom in and stuff. So here's the complete clock circuit. Now, if you notice, it has 3 different 555 timers. And as I recall, just from looking at them, this is the one that's the main clock source. This one has a push button switch, and so this is where we get single step mode, and this one has a mode selector switch, which is where we choose between single step or continuous mode. So this particular section here, and I've done, the 555 blinking stuff before, and this circuit, aside from different values for the timing, is, essentially identical. I mean, it's just a standard 555 astable configuration. And astable means that it's not stable in any mode. So in this case, it sort of tick-tocks between on and off. It just bounces back and forth between them forever while it's turned on. And the rate that it blinks is determined by these resistors and the capacitor here. And that can be calculated with the 555 timer calculator, which I've done in previous videos as well. So there's nothing really fancy here. So what this does is just runs at a certain rate. It's adjustable with this potentiometer, and then it pulses. And then it goes into this logic, this set of logic down here, which I'll talk about in a minute. The second 555 timer is really just here to debounce this switch, as I understand it. So when you push the button, it triggers the 555, and then how long it stays triggered for is determined by these 2 values. And again, there's a calculator for that. I think this is, well, let me just run it through the calculator. Okay, in monostable mode, using the values on Ben's schematic, it looks like it is about 110 milliseconds. Now, the purpose of that is just to debounce the switch. So when you push down the switch, they vibrate and they bounce a bit when they move. And, we can't really perceive that, but it's happening, right? And you don't want your clock pulses to be triggered. So the moment this 555 is triggered, it essentially starts its timer and it ignores all further input until the end of that pulse, at which point it returns back to an off state. So in this way, you should be able to push the button one time and step through your circuit, one clock tick. In the past, I debounced a switch using, I think it was a Schmidt trigger, and this is just a different way to do it, I guess. I don't think one is better than the other necessarily. In Ben's videos, I think he kind of intentionally used all 555s for this circuit because he was just trying to demonstrate using them in different ways. And since I have 3 of them left in my pack that I bought of 555s, I figured I would just do it this way as well. The third 555 in Ben's schematic for this clock is configured differently yet again. And as I understand it, this is in, I think, what's called a bistable configuration. And really, it's not really using like the timing of a 555 at all. I think these are just pull-up resistors here, and this capacitor here is just the one that's always recommended to be attached to pin 5. So really, it's just kind of a cheater to get at the fact that a 555 has some kind of a latch inside, like an SR latch. And I suppose if I had an SR latch chip, I could probably replace this whole thing using an SR latch. But anyway, the idea, as I understand it, is similar. It's also to debounce, essentially, because once it's triggered when it's in this configuration, it stays triggered until it's reset. So these 2 resistors aren't involved in timing at all, and all they're really doing, they're just pull-up resistors because they're connected to VCC, as you can see here. So in the case of how the schematic is drawn right now, switch position 3 is currently disconnected, but because it's connected through this 1K, there's 5 volts here. So that means that reset is being held high at the moment. And trigger is being held low because this position 1 is connected directly to ground. So that essentially overrides this pull-up resistor. So this might as well not be here. The trigger is currently being held low. When you flip the switch, the reverse happens. This one now has a direct short to ground, so reset is held low. And this one no longer has a connection to ground, but has to go through the 1K, which means it's held high, so this becomes high. Okay, so anyway, you might wonder why these 3 pieces and what do the outputs do? So the outputs in his circuit, they go down here to this set of logic. These are AND gates, this is an OR gate, and this is an inverter. And so in this case, the main clock, which just pulses continuously, goes down here and ANDs with this line, which comes from here. So essentially, this is the mode switch. So as long as this is enabled, this will be high, and then every pulse will be high here. That means the output's high. It goes into here, and since this is an OR, if this is high, and it goes into here, and this is also an AND. Now this is a halt signal. I'm going to skip that in my circuit. I don't think I need this, so I'm going to skip this line and this whole gate. So essentially my output will be here. When this switch is enabled, this timer, every time it clicks or ticks, whatever, that'll go through here and my output will be high. If this switch is off, then this is always low. And since that's always low, this one is an AND gate. It can never be high. So it doesn't matter how much this one ticks, this will never be high. Down here, on the other hand, this one is a different story because this one takes the now low signal, inverts it, it becomes a high signal. And now, whenever you push the button, it becomes high briefly. So that means that this one becomes high and the output becomes high, but only when I push the button and only for like that 110 milliseconds that this one stays in its unstable state, right? It only stays in that state for about 120 milliseconds or 110 milliseconds, and then it drops back to its stable state, which is off. So for that brief moment, this one's on, and that makes this true, and that means that the output has a pulse, but just one, very brief pulse. So anyway, I'm hoping that is roughly correct and makes sense. Again, you can, if you want to know the details from someone who knows far more about this stuff than I do, go watch Ben's videos. But for now, I will hook this up because I think I have all these parts. Actually, what I'll probably do is hook up each piece individually, make sure they work, and then hook up the logic. I think that's what Ben did, actually. But that makes a lot of sense because then you don't hook up too much stuff all at once and have to try and figure it out. Boop. Okay, I think I have the first stage hooked up. I'm going to apply power and we'll see if it blinks. Okay, no blinking. I must have something hooked up wrong. Let me take a peek at the schematic again. Okay, pin 1 is going to ground. Pin 2 is the trigger, and it goes to this capacitor, which in turn goes to ground. It does. Pin 2 also is supposed to go over here to pin 6, which it looks like it is. And then the other side of 6 goes into this leg of, I think that's right. 3 is the output. 4 is reset, and that should be held high, which it looks like it is being held high. 5 is the control voltage going through this small capacitor to ground, and it is. 6 is threshold. 6 is connected to pin 2, which we already established. 6 is also connected to the potentiometer, which it seems to be. 7 is discharge, which is supposed to be connected through this resistor into the potentiometer, which it seems to be. Oh, this is where I forgot. I forgot another resistor to VCC. 7 is wrong. I need another 1K resistor. Boop. Okay, let's try it again. I need to fix this switch. All right, so first stage works and is adjustable. Excellent. Now I'll hook up stage 2, which is, well, I guess not really a stage, but the second piece, which is the push button. Good, it's working. So for the mode switch, I need a switch that has 2 positions. Previously, I've used these dip switches, but they're only connected. They're either connected or not connected. I got these really tiny little switches. They're pretty hard to focus on, but they fit right on the breadboard. And they have enough legs here so that you can hook something into the center, and depending which way the switch is, it's either connected to this side or this side, rather than just disconnected or not. And this is also has two sets, which I believe that's called double pull, because there's 2 things you could connect to it, and then it's a double throw because it's connected in either direction. So I'm only going to use one side of it, but the neat thing about these is that they fit right on the breadboard. They don't fit across the hole, the gap in the center, but they do fit in the rows. So I think that'll work. And now I will hook up stage 3. Okay, mode switch seems to work. Excellent. All right, everything works, but I am noticing that I think I spaced these out too far because the schematic is going to need some logic chips, right? I'm going to skip this one, but I still need an inverter and 2 AND gates and an OR gate to get the result I want. And I have those chips, but that's 3 separate chips. So that's a bit frustrating. So that would be 3 separate logic chips on here, and all of my chips are multi-gate, so they're kind of big. That means that I don't have nearly enough room on here, I think. So I think what I'm going to have to do is I'm going to have to kind of rebuild things and compress it down. I wish I could just kind of copy and paste, but unfortunately I can't do that. So that's going to be a fair amount of work. I should have thought ahead better and spaced these a bit closer, but it is what it is, so I'll have to rebuild it. Okay, as you can see, I have moved everything over and I've rearranged how it's hooked up. So now I have my sort of control panel here in the center. So I have the switch here, the momentary step button here, and the potentiometer that adjusts speed here. And I have it arranged so that at least once the logic's hooked up, the slide switch will actually be in the direction of the function. So when it's slid to the left, The continuous timer will be active when it's slid to the right. The push button timer will be active. Now, right now, I just have the outputs all going to these LEDs, sort of similar to before. It's just that they're all over here, and just to show that the various parts still work. Now, I was looking on the schematic and noticing this pattern of gates here, 2 AND gates feeding into an OR gate. I ran across this one here. It's an SN74LS51N, and it's a dual AND OR invert gate. And so I kind of got to thinking. You can see that there's 2 ANDs, and it goes into an OR. The only difference is that this chip in the kit here inverts, and this one doesn't invert. Now, I don't know if that would actually make much of a difference, but I need an inverter for this part of the circuit, so I'm going to have an inverter anyway. So I could just use another inverter on my inverter chip to re-invert the output, and I think I can just get away with 2 chips instead of 3. Okay, actually, to make this maybe easier to visualize, I should point out the data sheet, of course. Here's the data sheet for that 451, or LS51, I mean, chip. And you can see the logic diagram is, you see what they're talking about, right? It's an AND OR invert. So there's 2 AND gates that go into an OR that's then inverted. And if we look on the schematic, I mean, that's, nearly the same symbol except for that trailing invert. So that's why I think that this is going to work. I mean, this should be pretty straightforward. I'll use this chip and then also the 74LS04 inverter for the 2 inversions I need to do. And all right, I'll get on it. Okay, I think it's hooked up. Let's see. Okay, it's partly correct. Something is slightly wrong, though. Continuous mode is good. When the switch is over here, it's coming through, and I can adjust the speed. But in momentary mode, that one's not coming through, so I must have something connected wrong. Okay, I got it fixed. I just had one wire was in the wrong spot. So now it works. So now my output signal is debounced from both the slide switch and the momentary switch, and I can switch modes. So this should be a very clean pulse over here. Awesome. Okay, so now I have my clock. The next thing I want to do is hook it up to a counter and put some LEDs on it, which by itself, not super interesting, but that's the last thing I wanted to get done in this video today, so I'm going to do that. I don't think I have enough room here, so I guess I need another board. This circuit is already big and it hardly does anything. All right, I clipped the boards together. That's very nice. All right, for this part, I'm going to be using an SN74LS191N, which is a down-up 16-bit binary counter. Okay, I just realized I've been thinking about this wrong. I got confused because the label for this chip said 16 counter, but I need 8 bits of counting, and these only count 4 bits at a time. So I do actually need to chain these or ripple them because I want to be able to have 8 bits of output because I want to ultimately address the 8-bit address on the memory chip and for part of my future undisclosed project idea. So I think I need to chain these to get the full 8 bits. So this will take a little bit longer than I thought, but I think it's just a matter of, hooking up the ripple, which I've done that sort of thing before on this counter circuit. So I think that should be pretty straightforward. So I'll just step through it and do it. I have a sliding switch here for the direction, up versus down. And the only thing I don't have is the ripple connected between these two, but I want to check and see if this works. They also start with garbage potentially, but that's fine. This side, I believe, is counting down. Yep, counting down in binary. And then this should count up. Well, it seems like it gets stuck there. I wonder what's going on with that. Could be floating inputs, or it could be I have something connected wrong. Let's check the other 4. Okay, see that to me seems correct. Pretty clearly correct. All right, I'm going to double check the connections again, but I wonder if something is just floating. Okay, I should be tying load active high for one thing. to avoid loading. Okay, I think it's working better now. Load may have been floating, causing it to reset occasionally to garbage. I think that's right, and they just so happen to have started on 0, so they're actually in sync, which is kind of nice. So now, to get the ripple to work between them, I think what I need to do is not have clock counting enabled all the time over here, but probably just have it enabled when ripple carry is true. I had figured this out before for my previous counter, and now I can't remember it. The counters can be easily cascaded by feeding the ripple clock output to the enable input of the succeeding counter if parallel clocking is used. I think my idea was right, so ripple clock output should go to the enable pin on the next one over, and that might do it. I just realized these chips are actually a little warm, which seems kind of surprising because it's not like they're doing anything very complicated. Possibly driving all these LEDs is bad. I don't know. Or maybe they just get warm. I'm not really sure at the moment. I'm just going to proceed and hope that everything's fine. Okay, let's see. Aha, there it is. All right. Awesome. I got lucky too. It started at 0. That's pretty nice. Okay, I think it's working. So now, if I turn off automatic mode and I pulse it once, I can step forward. Every time I push the button, it steps forward. And I can switch direction. Oh, that's interesting. What happened there? Now I can go backwards. Okay, I feel like I'm seeing bounce. I think I have to push this button quicker, perhaps, because, well, no, there's definitely bounce happening here. Ooh, not coordinated enough to do this with my left hand, apparently. Okay, so the debouncing circuit using the 555 is either not working quite right, or what else would that possibly be? I'm not sure. Maybe I messed up one of these capacitors in here or something and my timing is off. I might have to adjust some of the values there so that it's a longer delay, or I'll have to double check that to make sure that's doing what I think it's doing, but I think that's good enough for now. Okay, well, this turned out to take considerably longer than I anticipated. I'm not sure how long it'll be once I edit it down, but in my mind, this all fit nicely on one board. Clearly, not so good with the spatial positioning layout stuff in my head, I guess, but that's fine. Okay, that was fun. All right, so next time I will hopefully be able to proceed to the next part of my little top secret project. I don't know if it'll work because this, of course, turned out to be considerably more complex than I anticipated, so that probably means there might be yet another part to this, but hopefully it's, worth the wait once I get it going. Who knows? Maybe it won't even work. But hey, why not? It's fun, right? Okay, so I guess that's it for now. Hopefully this was fun to watch. I don't know. I mean, I feel like I didn't maybe explain very much this time around because I mostly made somebody else's circuit and then hooked it up to my counter, which is not maybe by itself very exciting, but a lot of blinking lights are always nice to see. Well, that's it for now, I guess. If you enjoyed it, thumbs up, subscribe. I'm getting very close to 1,000 subscribers, which is pretty cool. I mean, I don't think they give you a plaque for that, but hey, it's pretty neat. So I appreciate it if you subscribe. It's just nice to know that people are enjoying these, and hopefully I will see you next time.